My daughter is next to me, so you may hear her voice here and there. I hope she's not screaming.
Hi, Professor.
Okay, now I will first start with introducing you to chapter 1 and chapter 2. I know very likely you have not watched the lecture video. Okay, so before watching lecture videos, on chapter 1 and chapter 2, the one I mentioned in my announcement too, I would like you to pay attention. Please pay attention to this topic. So when you watch it, okay, there are a lot of things that they try to introduce you to statistic too. Okay, now the thing is, like, there are some key concepts that I think you need to be aware of and kind of like take a deeper look instead of just briefly listening to it. And those are the difference between statistic and parameter. Statistics and parameter. Okay, let me first say this. Statistic actually has two very different meaning. The statistic as a course, as a field, is a science, and I actually also say it's also an art. Statistic is a science and art of collecting data, organizing, summarizing, and analyzing, and inferencing. Informations. Okay, now collecting data, basically you do sampling. Now, once you collect the data, then you organize that, make it easier to see, easier to understand, and better to see, like kind of like pleasant to see. Okay, make it look interesting. That's actually part of that, though. It's actually part of that. So design graphic is actually part of what you would like to employ as a statistician. Okay, so one way to make people interested in your presentation is actually organizing your data in a way that it is appealing. Okay, organizing that's descriptive. Statistic together with summarizing. So these two parts here are now analyzing and inferencing. That's basically the later part that we do after we talk about probability. Okay, now what is inferencing? Inferencing basically making decision. Okay, that's inferential statistic. Okay, now that's statistic as a course, as a field of study. Now, statistic and parameter that I need you to pay attention to when you watch the lecture video, and this is actually from 1.1, is the following. We have population, and we have sample. Population is the collection of all objects. That's the collection of all objects in the context. I'm sorry, not statistic, sample. Now, sample is only part of that. Sample is part of population. So you will see that population is unique, yet sample is not unique. We say, for example, the population of all students at West LA College. Then as long as you are a student at West LA College, you are part of the population. Okay, now the thing is when we say we sample 100 people, then when you sample 100 people, you get 100 people. When I sample 100 people, I may get different group of 100 people. Okay, and somebody else, when they do sampling 100 people, they may get different group of 100 people. You see what I mean? And there could be some overlap, right? But population is unique. When we talk about West LA College students, then either I do it, you do it, anybody do it, we should get the same group. Okay, now when we do sampling, then your sample and my sample may be different. Okay, now what statistic as a field trying to do is trying to say something about the population, analyze the population from the sample. So instead of like asking every students at West LA College, we only ask some students, yet the result of our observation of these some students hopefully represent what the population actually say. Okay, so for example, if you want to know, is this distant remote learning is something our population would like to continue doing? Okay, is it something, even if the pandemic already fade away, right? And do you want to go on with this? Then we do survey, right? Okay, now you can ask everybody, okay? But of course, some people will say yes, some people they say they don't like it, you know? Okay, now, but for you to ask everybody, like 60,000 students, will be very, very time consuming. And the result you get very likely will not be different from if you ask only, let's say, 3,000 students, or maybe only 400 students. Okay, so if we will get the same result, what's the point of asking everybody? You see what I mean? Okay, so the thing is then, the result we get from population is called parameter. So for example, population mean, now that's called parameter. Now sample mean is called statistic. Okay, sample mean is statistic. Now population, for example, population size. How many people in the population? Now that's a parameter. Okay, now sample size is a statistic. Basically, when we say parameter, it means that's the measurement that comes from population. When we say it is a statistic, then it's a measurement coming from a sample. Okay, now, so you see that there's two different meaning of this word statistic. You may say, Thomas, it's confusing. Well, it happens. It happens. Okay, it happens. It's not something never happened in our, even in our English though. Give me a second. Give me a second. my wife's home. So good. Okay, so statistic is basically the measurement that we get from sample parameter, measurement we get from population. Okay, now the word statistic, like what I mentioned earlier, has different meaning. And you may say that's confusing, but it's actually not really. It's not the first time it happened in English. Okay, in fact, in English, I can identify two words that have totally different meaning. So the word statistic is just another statistic to that statistic, okay? What words? The first word is the word right. The word right has at least 4 different meanings. Can you tell me what are those?
Direction.
Right, the left, right, right? The left, right, and then what else?
Making a right decision.
Right decision is correct decision. So wrong, right, wrong, right? So the wrong decision, right decision. What else? The word right also means what? Right as a privilege. Do I spell it right? And there's another one word, one meaning of the word right. The word right as the 90-degree angle. The right angle, right? Okay. Now, so a word with multiple significantly different meaning is not something just first time happened in English. So we should not say, oh, so confusing, statistic has 2 different meaning. No, the word right that we use basically on daily basis also has actually multiple meaning, right? And actually another one is the word mean. The mean as what do you mean, right? What is your intention? That's one.
Behavior.
Okay. Behavior, a mean behavior, mean as in being kind of like evil, right? Behavior, bad behavior. Okay, and the word mean as in statistic, it's like the sum over count, the total divided by the number of objects, right? Okay, so we have at least 2 different words that that has multiple meaning, and it's actually not only these 2, including the word statistic, only 3. No, there are actually a lot. There are actually a lot of words in our English vocabulary that has multiple meaning. Okay, but I pointed out to you to realize that when you later on watch the lecture video, be aware that these 2 different meaning of statistic will come from the same section, as if they are in the same topic. Okay, but they are actually talking in different contexts. Okay, now that's one. Second thing that you need to pay attention when you watch that lecture video is the difference between qualitative and quantitative. Quantitative. So only one letter different, qualitative and quantitative. Now, but the root word, the quality, means it's more into something we cannot measure by numbers. Quantitative coming from the word quantity, right? Related to quantity. Okay, by numbers. Okay, and then quantitative basically based on some characteristic or attribute. Now, so why we need to be able to distinguish this. It's actually not too hard to distinguish. For example, the following is qualitative. For example, car brands, the brands of cars, Toyota, Honda, Mitsubishi, BMW, Mercedes-Benz, Porsche. Okay. Now, basically qualitative because we cannot add them. It's like you cannot say, oh, what is the average of BMW and Honda? You cannot add BMW plus Honda divided by 2. No, you cannot do that, right? Okay. Or for example, race, nationality, which country you come from. I come from Indonesia. You may be born in America, somebody else born in Mexico, somebody else born in Russia, for example. So on average, what's that? Well, we cannot just add them and divide. Okay. So you will see that in long run, we will deal with quantitative data and variable in statistics. Okay, and how do we deal with qualitative data, qualitative variables? Then our textbook also mentioned that. Okay, now when it is quantitative by numbers, we have more separation here, something called discrete and continuous. Discrete, continuous. Now, discrete numbers, for examples, 1, 2, 3, maybe some fraction, but not all fractions. Okay. For example, the quantitative, discrete data, like the number of siblings, the number of people. Okay. The number of people, how many children you have, Thomas? I have 2. Now, you see that's discrete, right? Why? Because I should not have 2.5 children. I should not have 2.3. I should not have 1.7. No. Okay. Now, continuous is basically in sense of an interval. Sense of interval. I think I better say it this way. Discrete doesn't have to be an integer. Like shoe size, your shoe size, for example, your shoe size, mine is 42, somebody have 43, but somebody may have 42.5. Okay, now, but so it's not necessarily say that it has to be integer, no. But we know that it is discrete if we can find 2 numbers. Okay, we can find 2 numbers without any in between. Thomas, what do you mean with that? It's kind of hard to explain, but it's like this. Shoe size, for example, we have 42, we have 43, but you can find 42.5, right? Now, the thing is between 42 and 42.5, there is no shoe size in between. No shoe size of like 42.3. Now, once you are in this kind of situation, then you know the data is discrete. Okay, if you can find 2 numbers without and no numbers in between. Okay, how many children you have, Thomas? I have 2 children. Somebody else have 3 children, but nobody will have 2.5 children. Okay, now continuous is like, for example, the length. How tall are you, Thomas? I'm 6'10". Okay, and you may be, let's say, 6'11". Okay, now, but we can easily find, maybe not that easy, but we believe we can find somebody 6'10.5", right? Or 6'10.7". We can find it. You see what I mean? Okay, the length, the distance, the weight. Okay, the weight. Like, for example, I was sending a package to my friend in Northern California, and the weight was 28 pounds. Okay, now somebody else may send something 28.7 pounds. Okay, but if I pull something out, then it may becomes 27.9. You can come up with a weight, any weight between any two numbers. You can pick two numbers, and you can pick two numbers, and then the weight, any weight in between those two numbers is doable. Now, then it is continuous. Okay, length, weight, also time, right? 1 second, 2 seconds, 1.5 seconds, 1.7 seconds, 1.675 seconds, so on and so forth. Okay, now that's about the qualitative, quantitative measurements. And then actually the following is the continuation of that type of separation: qualitative, quantitative, discrete, continuous. And in fact, this is actually more important about level of measurements. Levels of measurement. In statistic course, especially at this level, we follow 4 levels of measurements starting from nominal. So this is the lowest level, nominal. And then the second one is ordinal. The third one is interval. And the fourth one is ratio. Now let me explain a little bit what is this level of measurement. Nominal measurement is basically just a characteristic or attribute. Basically, that's qualitative. Almost to the point of qualitative, but I think I cannot really say it that way either. For example, which country you come from? United States, Mexico, Indonesia, Japan, Russia, okay, Nigeria. Those are nominal. Okay, what car do you drive? Okay, what computer do you use? What brand do you use? What phone do you use? Okay, that's nominal. Okay, so when we list that, like for example, when I try to list, okay, the car brand, let's say car, the type of car you drive. So how many people use Honda? Let's say 3 people. How many people use Toyota? Let's say 4 people. How about how many people use Tesla? Let's say 7 people. Okay, now the thing is, among Toyota, Honda, and Tesla, at least that we cannot add them. Okay, we cannot add them, we cannot subtract, and especially when we talk about race, for example, we should not say, well, this race is better, that race is worse. Okay, Asian, so let me change that. Okay, Asian, Hispanic, white, black. Let's say there are 5 of us here, the frequency. So instead of car, I'm sorry, change this to heritage maybe. Okay, now the variable of being Asian, black, Hispanic, white, we call that nominal because we cannot put them in order. We cannot say, oh, you know what, Asian should come first, then black. Why? Well, simply because it starts with an A? No, okay. Well, I list them in that order here, but doesn't mean Asian is better. No, not in that sense. Okay, we cannot put that kind of a concept of which race is better, which race is worse. Okay, now that's why when we talk about which country you come from, what's your heritage, what's your race, then it will fall into the level of nominal measurement. Now, ordinal, the root word from the word order means you can put it in order. You can put it in order. Now, of course, earlier I used the illustration cars. Some people may put cars in order. Okay, like some people say Honda and, for example, BMW. Which one is better? Almost all the time, BMW is better, right? Okay, so if I say, oh, you know what, there are these cars, Hondas, BMW, and then Tesla, and then Mercedes-Benz, then can you put them in order? Somebody may come up this way. Oh, you know what? Honda, among these four, Honda is actually the lowest one. Okay, and then Mercedes-Benz, and then BMW, and then Tesla. Of course, this is very subjective. Okay, this is very. Somebody else may say, oh, you know what? I prefer BMW than Tesla. Okay. Somebody else, like if you ask me which car I would like, I like Honda, by the way. I like Honda. Okay, so to put all of this in order, okay, then Mercedes-Benz is the lowest one for me. BMW is the second lowest. And then Tesla, Honda is the best. Do you know why? That's why I say it's subjective, right? Because it's the cheapest. Cheapest to buy, cheapest to maintain. Okay, and then it's also gas saving. Okay, yes, Tesla is gas saving, but it is too expensive to buy to start with. Okay, and I heard that to maintain that also it's not cheap. Okay, BMW, it's actually ultimate driving machine, so yeah, there's a trade-off. Okay, so what I'm saying here is very, very subjective. Okay, I'm just trying to show you that when the level of measurement is ordinal, means you can put them in order. Okay, you can put them from the lowest to the highest. Now, another example of ordinal measurement is, for example, the rank. Not the first rank, second rank, third rank only. Yes, it is ordinal also. But I'm talking about, let's say, military rank. Okay, the highest one is general, right? And then if we have colonel, we have surgeon, right? Okay, of course, we cannot say, oh, there are 3 people in that room, surgeon, colonel, and general. What's the average? We cannot do average in the sense of adding and then dividing by 3. Okay, but we can put them in order. Okay, what is the lowest rank going to the highest rank? Now, interval, you will see that interval almost, as far as I know, interval always numerical. So you may have qualitative here, maybe qualitative, but the one here always quantitative. Always numbers. Now then, it is possible that ordinal also have numbers. Okay. In fact, I see one case where the nominal measurement actually made of numbers. For example, zip code. Zip codes actually nominal. It's like, where do you live? What's your zip code? Oh, this is my zip code. Oh, my zip code is, I'm from Seattle, so it's like I don't know what, let's say 95721. Does it mean that 95721 is better? No, never imply that way. It's just numbers to identify something. Okay, and in fact, it doesn't really represent your position. Who is actually more to the north? Who is more to the south? No, there's no such arrangement. Okay, now your house number maybe, okay, if you live on the same street, okay, if you live on the same street and then your house number is 620 and then somebody else live at 840, for example, then you know that it doesn't mean 840 is better. Not that's not in sense of that's not in sense that you can add and divide. But yes, if you go from the smallest number to the largest, then you will meet this first and then that one. So in that sense, the house number on the same street is actually ordinal because you can put them in order. Okay, but zip code is not. Okay, now how about interval? How about interval? Now interval, for example, interval, for example, IQ score. Another one, your GPA, for example. Okay, now IQ score, for example, let's say my IQ score is 90 and then your IQ score is 100. When it comes to interval means you can subtract them. So there's a difference. The difference between my IQ score and your IQ score is 10. Okay, I'm 10 points below your IQ score. Okay, now let's say I change it, becomes my IQ is 90 and then your IQ is 180. Okay, the difference is 90, right? The difference is 90. But does it mean that you are twice smarter than me? No, actually no. The fact that I'm 90, that's below average of 100. Okay, and the fact that you are 180, that's very, very, very high. There's a chance that you are actually at least 20 times smarter than me, even though the IQ score seems to be only twice. Okay, so IQ score will not fall into ratio because the ratio does not mean anything. The ratio is meaningless. Okay, the difference is meaningful, but the ratio is meaningless. Okay, likewise, the same thing with GPA. The same thing with GPA. Let's say my GPA is 2.0 and then your GPA is 4.0. Okay, what is the difference? Well, 2.00, right? That's the difference. Okay, but does it mean that you are twice smarter than me? No, actually you can be 100 times smarter than me, but the highest GPA you can get in college is 4.00. Therefore, you already break the curve. There's no more grade available for you other than better. There's no more grade better than an A, right? So you can be super smart. Okay, you got an A, and somebody else smart enough to get an A, barely an A. It won't reflect from the GPA. You see what I mean? Okay, and likewise, test score too. Test score, your test score, for example. Okay, I may get 30 points and you get 60 points. For example, both of these are failing, of course, but you cannot say that you are smarter than me. No, no, this is, I get 30, that must be really, really bad. Okay, I must be really, really bad. Okay, you get 60, that's still not passing in this case, but you are close enough. Okay, if you get 60, let's say you get 60 in my class, which is not good, of course. If you get 60, I will tell you, you know what, repeat the class. Okay, but if you get 30, I will say, you know what, go back home, think about what you really want to do, because the fact that you get 30, it must be because you don't study, you don't apply yourself. Okay, you have something else more important than your education. You know, so the way I treat people who get 30 and then get 60, of course, different. I will not tell people who get 30 to study twice more, twice harder to get 60. No. Okay. If you get 30, if Thomas get 30 in this class, okay, studying 3 times harder doesn't help. No, it must be more than just studying more. Okay, there must be another aspect that make me not performing even close to passing. So IQ score, GPA, test score are actually in the interval. One more, temperature. In degree Fahrenheit, and degrees Celsius. Why we say so? Because, for example, 50 degrees Celsius and 100 degrees Celsius, okay, it's 50 degrees Celsius difference, but we do not say that 100 degrees Celsius is twice warmer or twice hotter compared to 50 degrees Celsius. Actually, 50 degrees Celsius is really, it's very warm. Okay, or let's change this to Fahrenheit. I think Fahrenheit will be, I come from Indonesia, we use Celsius there, but Fahrenheit I think is still easy to explain. 50-degree Fahrenheit is pretty cold, right? Okay, 100-degree Fahrenheit, I think that's hot. Now we do not say 100-degree Fahrenheit is twice hotter than 50-degree Fahrenheit. No, we don't say it that way. Okay, we say the difference is 50-degree Fahrenheit, but we do not say that 100-degree Fahrenheit is twice hotter. We do not say that 50-degree Fahrenheit is twice colder compared to 100-degree Fahrenheit. Okay, so you see that it's numerical, it's quantitative. Okay, only the difference meaningful, but the ratio is meaningless. That's for interval. For ratio, then when we take the quotient, it's still meaningful. For example, my son is 3 feet tall, I am 6 feet. Then you can say that I am twice taller than my son. Okay, or for example, a car that is $20,000 and then another car that is $60,000, then you can say that not only the difference is $40,000, it is 3 times more expensive. Yes, we can say it that way. Okay, now, so when you watch the lecture video, pay attention to this detail further later on. Okay, the difference between interval and ratio. Now, one of the consequence of this is, and I think our textbook nor our lecture video mentioned this, that only when it is interval or ratio measurement, you can do histogram. Now, what is histogram, Thomas? You will see that in chapter 2. Okay, you will see that in chapter 2. Now, if it is not interval or ratio, if it is nominal or ordinal, then you cannot do histogram. The most you can do is actually bar graph. Now, there are different ways to present the data. Okay, bar graph, histogram, line graph, pie chart, pictograph. There are a lot of ways to present the data. But when it comes to histogram and bar graph, we cannot use histogram. We cannot use histogram for the data that is not in at least interval level measurement. Okay. By the way, this is only for 1.1 though, but that's actually the most important part of chapter 1. Now, then when you go to 1.2, you will see about the difference between observational study versus design experiment. And what's the difference between these two? Okay, when we collect data, there are 2 major ways to collect data. First one, observational studies, basically coming from the word observe. You only observe, you only look at that, measure this, measure that. Now, design experiment, on the other hand, you may tweak, you apply certain stimulus or stimuli into the objects. Now, for example, observational studies. Okay, observational studies, for example, Of course, you still need to watch the lecture video, right? The example of observational studies is this, like you compare people, the incomes of people in STEM program and the income of people in non-STEM program. And of course, the data that we get right now is like people in STEM program, science, technology, engineering, math, tends to have higher pay compared to non-STEM program. Okay, now how do we get these numbers? Oh, from observing. What do? You ask people working in STEM program, okay, in STEM field, and you ask people working in non-STEM field, right? But you only observe, okay? You don't tweak any, you don't provide any stimulus. Now, design experiment, for example, you want to see the effect of, let's say, some kind of after school program, or maybe SAT prep, if you know what SAT is, right? Okay, so you compare some students before they took SAT prep, the group of students, how they did in taking SAT test, and then after that you provide them with SAT prep, and then after SAT prep you see how they do again. So this way we can see the effect of putting our children into an after school program. Will that improve his or her performance at school? Okay, when you put somebody into SAT prep, of course, the expectation is the SAT score will improve, right? Now, so how do we measure that? Then we use design experiment. Why? Because you provide some tweak, some stimulus into the object of your observation. So you don't only observe these students, but you do something to them and see how it changed. Okay. Now that's the difference between observational study and design experiments. Of course, there are more details into that though. Okay, there are more details into that. In 1.3, oops, wrong color. 1.3, we talk about sampling. I'm sorry, I can't really see this thing. Okay, sampling. We talk about sampling, and then in the sense that will our sampling method be with repetition, without repetition? Okay, sometimes we call that with replacement or without replacement. Now, 1.3 is very closely related to 1.4. It's closely related. So other textbook actually put them in the same section. So sampling from one point of view is, when you do sampling, will you allow to select the same object again? If that's possible, then you call that with repetition. Okay, now if you don't allow to get the same object again, then we say it's without repetition. Let's say the following. Suppose you have a container, right? And then you put a penny in there, and then a dime, and then a quarter. Okay, and then you kind of like shake it a little bit, okay, and see which coin will come out first. Okay. Now, of course, this is with repetition. You need to do it many times, such that you can come up with a conclusion that, for example, 60% of the time, quarter will come out first. Okay, and then 25% of the time it will be dime, and then the other 15% of the time it's penny. Okay, but the thing is, like, when you shake it and have one coin coming out, it is possible that it's the same quarter coming out 600 times out of 1,000 times shaking it, right? So this is with repetition. Okay, but in other case, you may have a sampling where you will not get the same objects coming out again. Now, 1.4 is the how to obtain sample. Our textbook lists four ways, and only 3 of them actually allowable. Okay, the first one is called stratified. You figure out, you see later on what does it mean, stratified. Okay, and then the second one, systematic. And it's the word systematic is a bit misleading. It doesn't mean stratified is not systematic. It's just like systematic in one sense later on. And then cluster. And the last one is by convenient. Now, this is not an acceptable way to get sampling, to get our sample. Now, what is stratified method, systematic method, cluster method? Now, let's say we have 1,000 people that we need in our population. Okay, now systematic method is like, for example, you decide, you know what, I need a sample of 100. So I will take every 10th people. So let this 100 people walk through the door, and the 10th person will be in my sample. The 20th person will be in my sample. Every multiple of 10th person will be in my sample. Or you can also say, you know what, I will pick every 5th person. Okay, now that's a sampling method. Basically, you pre-decide how you will sample number, what will be, how to say that? Not sample number, what? I should say that object number, what will be in your sample. Okay, from that population, you line them up, object number what will be in the sample. You can also say that I will pick everybody, the first, and then the 5th person, the 9th person, I keep on adding 4. So the first person coming through that door, I will ask his age, and then the 5th person, and the 9th person, and then the 14th person. I'm sorry, I will add 4, so 13th. Okay, so the 13th person, what's your age? The 17th person, what's your age? How about the 18th person? No, you are not in my systematic count. Okay, I only get every 4n plus first, for example. Okay, now that's called systematic. Stratified is as the following. I see this actually, somebody illustrate this way. Let's say this is your population. Okay, let's say that's your population. Stratified is this. Basically, you make them into clusters. Okay, you divide them not necessarily in area sense. You just divide them into groups. Okay, and then from each group, you select, you sample each group. Let's say from each group, you take 2 people. How you get those 2 people, you may do it by systematic method. You may do it by another stratified method, you can do it by clustering method. Okay. Now, stratified method, basically, you put them into classes and then you take a sample from each class. From this class, you take how many people, from how many people, from here, how many people, from here, how many people, from here, how many people. That's stratified. What is clustering? Very similar to stratified. Okay, very similar to stratified, but stratified is basically you break it into classes first, non-overlapping classes, and then you randomly select some of the cluster, some of the states, or some of the class as your sample. Okay, so instead of choosing 2 from each class or how many people from each class, instead of doing so, I separate them into classes. And then I say, oh, you know what? I want to ask everybody from here and everybody from here. Like that. That's what clustering means, clustering method. Okay. Okay, so once I separate them into classes, okay, I then decide I want to take everybody in this class and everybody in other class to be in my sample. So the difference between clustering and stratifying is that both of them, the same thing is, both of them separated into classes first. Now, stratified method will have some people from each class. You will have some people from each class. Okay, that's stratified. Clustering method, you will get all people from some class. Now, let me write it down so that you see the difference. When you see examples from the lecture video later on, you will get, I hope you become clearer. Okay, stratified means you get some from all class, all classes. Let's say you have 50 states, right? And you want to sample people's income from the whole United States. So you from 50 states plus Washington, D.C., you will grab some people from California, some people from Nevada, some people from state of Washington, some people from state of Oregon, some people from state of Michigan, some people from state of Texas, so on and so forth. Okay, now clustering method will take all from some. Clustering method is taking all from some classes. So even though we have 50 states, then you say, you know what, if you really want to know who get like this is a classic case for our presidential election. If you really want to know who get the presidency, you just need to ask people in Michigan, for example. Okay, for example. In other words, why do we need to waste our money and time to do the presidential election in all 50 states? Just do it in Michigan. Why? Because historically, whatever Michigan decides, that's what that's the president to be, you know. Okay, so that's what it means, like a clustering method. Okay, even though I don't agree with that. No, don't do it that way. But instead of asking some people from every states, okay, if you want to do a shortcut in knowing, if you like, you are betting, you are gambling on who will be the president. I was one. Okay, I love gambling, by the way. Okay, it's simply because my wife, then I don't gamble anymore now. So if I need to gamble, I want to gamble and decide who will be the president, then I will actually look at the data from Michigan, for example. Or is it Michigan or Ohio? I kind of like don't remember precisely. Okay, why? Because it turns out that Michigan population configuration, people in Michigan, the way it is, the configuration, the people body there, the structure of people there, quite representing the whole United States when it comes to which president they would like. Okay, so clustering method, however strange you think it actually makes sense in some cases. Now, it does take some wisdom to decide which method is best in what case. Okay, now that's for 1.4. When you go to 1.5 and 1.6, they describe a lot bias in sampling. Things that we need to be careful when we do sampling, such that the data we get is not biased. Okay, for example, it is not appropriate for me to ask. When I say not appropriate, in the meaning that the result I get will not be the true proportion. For example, if I ask, how many of you here actually repeating the class? Okay, now the thing is, like, some people, including me, if I am repeating the class, I don't think I'm going to raise my hand. I will just pretend that I don't hear what you ask, or I don't understand what you ask. Okay, why? Because the question may be the teacher may be have no intention to embarrass you. Okay, but other students, when they heard that question, then other students will look around and say, hey, who is repeating this class, you know? Okay, so that's not a question that's not how you want to ask that question. And whoever asks that question will not get the true result. Okay, so even when we ask question, we need to be careful. Okay, one of the most biased, and I consider this kind of like very political. I'm telling you one of the case that happens like around 8 years ago, the case of Obamacare. How partisan politics get into our society, so deeply dividing us. Obamacare and Affordable Care Act. They ask this question: which of these two you prefer, Obamacare or Affordable Care Act? If you ask this question to Democrat, for example, majority of them will choose Obamacare. I make up numbers, okay? I make up numbers. And only 30% of them will choose Affordable Care Act. Now, if you ask Republicans, people with Republican affiliation, okay, let's say I make up numbers again, only 20% will choose Obamacare and 80% choose Affordable Care Act. Unbeknownst to them that Obamacare just a nickname for the formal name Affordable Care Act. I mean, they're just the same thing. They're just the same thing. It's just like, who do you prefer, Mr. Harjuna or Thomas? Okay, Thomas is my first name. Mr. Harjuna is what people call me formally. Okay, who is the better teacher? If you say Thomas, it means you don't know Thomas at all. If you say Harjuna, then you don't know Harjuna at all. It's like these people, they don't know anything about these. Obamacare is just basically Affordable Care Act. Okay, that's how deeply divided our country, even during Obama time. Okay, now I don't put the blame on him. Okay, don't get me wrong. It's like, it's not Obama's fault. No, this country is so divided because you and me are thinking too much and too negatively about other people. Okay, and some people judge from the name. Oh, because it's Obama, then I support it. And Republican actually on the other side. Oh, because it is Obama, I don't like it. What's wrong with these people? Okay, they don't even read what is that act about, of Affordable Care Act. Okay, so that's why I say that bias in sampling. Okay, when you do sample, when you put certain name, some people get pushed away because of name. Some people actually get pulled in by that name. Okay, so be careful with the terminology you use when you do sampling. Okay, now 1.6 is more into, no, not one. Oh, I think I saw it wrong. Is it 1.7 instead? Oh, I'm sorry. No, I think it's 2.4 instead. Yeah, 2.4, not 1.6. Has something to do with bias in sampling also, but 2.4 is misrepresentation of data. Misrepresentation of data is actually the place where a lot of people who call themselves statisticians try to tweak your opinion by purposely misrepresent the data. Okay, I'm not saying that they represent the data in the wrong way, but they purposely represent that in certain way that it gives you different feeling. Okay, so for example, let's say my GPA is 2.9. Hold on, give me a second. Let's say my GPA is 2.9. This is 3, so Thomas GPA almost 3, right? And then your GPA, is 4. And because nobody have GPA less than 2, then that person start from 2. Now, the thing is, like, when you draw it this way, it seems like your GPA is twice, at least, it's more than twice higher than mine. You see what I mean? Okay. Now, I'm not teaching you that this is, I'm not saying that this is wrong, even though it is, they call this misrepresentation, but this is where we get more, you may want to call that political. Okay. If you have certain agenda, if you want to say that your GPA is better than Thomas, you will try to depict your GPA to be very different. There's a big gap. You try to show that there's a big gap between your GPA and my GPA, to the point that it is twice. But it's actually no, you don't start from 0, you start from 2. Now, on the other hand, Thomas may depict that this way. I start from 0, 1, 2, 3, 4. Okay, and then Thomas GPA is here, your GPA is here. Okay, now you see the gap here is not that big, right? The gap here is not that big. So which is the right one? Nothing is the right one. I don't want to say that the one I just did right now is the right one. No. Okay, no. Why? Because when I present certain data to you, okay, I have a certain agenda. My agenda is I want to show that, for example, that your GPA is a lot higher than mine. So I will show it this way. That's the right way, because that's the one achieve my purpose, my agenda. Okay. While if I want to show that there's not a big difference, I don't even think this is a good idea. I will do it this way. I will do it this way. I will do it like, okay, this is 0, 1, 2, 3, 4. And then Thomas is here, 3. Yours is 4. Right? So you see just even smaller difference, right? As if 3.0 and 4.0 is just not too far. It's only 1 point off, right? But in reality, 4.0 and 3.0 is very, very big difference. Okay, but it is also not true to say that 4.0 is twice better than 3.0. That's also not true. Okay, now what I want to say here is from the section of 2.4, misrepresentation of data, you learn how you can depict in the data in a way that it gives different feeling to the reader. Okay, that's where you can be creative. Okay, now again, I don't want to say it's a wrong way. Yeah, people will say that Thomas is a wrong way to do certain things, but the way I see is like what is right, what is wrong depends on what you want to achieve. Okay, there's a right way and wrong way to do something. Okay, we don't judge the right and wrong in this case based on only what the textbooks say. Oh, this is a misrepresentation. No, the way I see in practice, it really depends on do you achieve your goal or not. Okay, so it's two things though. From science point of view, of course, representing it this way, the way I showed you earlier, representing it this way, that you start from 2 and then 3 and then 4 like this. Of course, this is a wrong way. Okay, but in reality, in real life, if depicting your graph this way make people believe you, then just do it. Okay, again, I'm not here to teach you moral. I'm teaching you how to use statistics. Okay, my job is not to teach you how to use statistic according to what I think is moral, because what is moral for me may not be moral for you. Okay, the issue of lockdown. The issue of lockdown is a very, very difficult issue. Now, I'm sorry if this is sensitive for a lot of you. I try to present to you two different points of view, and the result is quite opposite. Okay, those people who support that doing lockdown has an honest concern that our pandemic, our COVID-19, is actually that's the way we can tackle COVID-19. Do a lockdown, even strict lockdown in some countries, so the pandemic can fade out. Okay, now, but some people say if you do lockdown, who gonna pay for my rent? Who gonna pay for my expense? Because we still need to eat. Okay, no lockdown. Now, by the way, most people actually agree with certain level of lockdown. Okay, but people who say no lockdown, okay, they worry about, like, if you lock me at home, like I cannot go out, right? I cannot go out. Then I will stay home doing nothing, worry about this, worry about that. And there have been some cases of suicides in some countries. And that's real though. Okay, that's real. We should not say that, you know what, it only happened to some people. You can do further lockdown and you will see more people commit suicide. And I'm talking from a perspective of somebody who has depression. Okay, you cannot say that depression is just a mind problem. No, it's real. Okay, and we have more and more people fall into depression. So if we don't do lockdown, then people may get sick because of COVID. But if we do lockdown for too long and too strict, people may get sick mentally. Okay, and I may be one of them. Okay, I'm not saying that only other people get this. No, including me. I get bored to stay at home. I want to go out, but because I have children at home, then it's just like I worry a little bit here and there. Now, the good thing with me is I still can teach from home. Okay, my income still stable. But how about our colleagues, our neighbors, our friends who don't have that privilege? I worry about them. Okay, so that's not an issue that easy tackle. How about restaurants. Now I live in Monterey Park and a lot of restaurants, cafe around here. Okay. Uh, and of course, there are a lot of students. I live nearby East LA College. So there are students actually working in these cafes, and they rely on tips to support their study, to pay for their rent. Okay. So it does affect my students too directly. Okay. Now, then the thing is like if one of these people or this organization who support uh, that to dine in the restaurant, then I will purposely represent the data. I will pick and choose, honestly. Okay. I will pick and choose the data to show the support that dining in a restaurant is still safe, right? Even though that may not be right. Okay. In other words, misrepresenting the data from that section, when you study this section, don't see that from how it is misrepresented, but see that from how you can be creative in presenting your data so that the listener, the viewer, be attracted to the concepts, the idea that you try to present. Okay. Now, in 2.1, organizing data, qualitative data. So you will see the type of method to organize the data, bar graph. So pay attention to how to read, at least how to read bar graph. There's horizontal bar graph, vertical bar graph, and doesn't matter. There's another one called Pareto chart. That's quite commonly used. Okay. Now you take a look also what is Pareto chart. Pareto chart is actually a type of bar graph. This is a type of bar graph. Also pie chart. Okay, throughout my lecture, I will try to present to you which chart is more appropriate in what situation. For example, pie chart is usually used when you have nominal data. Okay, nominal data, and pie chart usually being used if you want to show a portion, to emphasize on portion. Like for example, if you want to show how many students impacted negatively by remote teaching or positively by remote teaching, then it is better for you to present that using pie chart, because it gives you a better feeling on, oh, not only about the percentage, right? Okay, not only about the percentage, but you can see here, hey, you know what? Most people affected negatively compared to the students who actually affected positively. Okay, now pie chart is more appropriate. Instead of saying that negatively 60%, affected positively is 40%, writing it in numbers this way doesn't give you too much feeling. Yeah, it's 60% is more than 40%, but how much bigger? Okay, once you put it into pie chart, suddenly you have a better feeling about it. Okay, hey, you know what? It's larger and it's a lot larger. Okay, for example, now I actually don't know if the portion of students affected negatively or positively by remote teaching. Okay, if people ask me, Thomas, what is your opinion? My opinion is I will, at this time, is just still do it remotely, but how will we start coming back to school? I will start opening the school. If people ask my opinion, okay, this is my opinion and it doesn't have to be the best one. No, I think about this a little bit, but this is what I can offer. That very likely somebody else can have a better opinion. It's like, okay, the instruction is still done online, but then when it comes to test, then we do it on campus. Okay, and then of course we try to arrange in a way that when we do the test on campus, not too many people coming to campus at once. But at the same time, the reason I want students to do the test on campus, so that we don't have a big issue about how to proctor and how about the students' privacy that, of course, we need to protect too, right? Okay, that's for 2.1, 2.2 about quantitative data. Quantitative data, popular display or histogram. Okay, of course, using tables, that's another way. Contingency table. And then in 2.3, there's another display, polygons, cumulative frequency, relative frequency. Okay, things that is good to know, but I will not ask anything from chapter 1 or chapter 2 in my quiz nor in my test. I promise you that one. Okay, however, if you don't study, you don't even watch the videos, then when we work further later on, you will have harder time to grasp why do we have to do it this way? Why do we have to do it that way? Okay, so this provides you a, I hope, a firm and good foundation on going further in this course. Okay, it's just by you can really earn this knowledge by watching the lecture video, and maybe you flip some pages from your book. Okay, please do this maybe by Monday. Monday we don't have class, by the way. We don't have class on Monday, so please use that time to watch these videos for chapter 1 and chapter 2. Okay, if you ask me, Thomas, you know what, if I only have 30 minutes, which section should I watch? Okay, the one I really need you to watch is 1.1, 1.1, and then 1.4, 2.1, 2.2. Let me make sure. Yes, like if you really say that I don't really have time, Thomas, then what do you need to watch? Watch this. The topics from 1.1, topics from 1.4, 2.1, and 2.2. For anything you can watch more, it will be great. Okay, it will be even better. Okay, now let's go on with 3.1. Again, my assumption is you already watched lesson 1 and lesson 2. Now, then I will put more details into our discussion here. We will do problems from 3.1. Notation. Population mean. Because it comes from population, then it is a parameter. Is denoted by mu. It's denoted by mu. Learn to write this. Okay, it's like a curvy. It looks like U. Maybe you can think of it this way. It looks like U. Okay, but then you put the left leg longer like that. Okay, that's population mean, mu. Sample mean is denoted by X bar. Now, the way to compute them happens to be the same. It's the sum of all data divided by population size for population mean. For sample mean, it's the sum of all data divided by sample size, where population size denoted by capital M, capital N, and sample size is denoted by lowercase n. Okay, now big warning, big warning. Population size is by capital N. Sample size by lowercase n. Okay. Now you do not say, Thomas, this is my capital N. No, that's actually sample size that you write big. That's a big baby, but it's still a baby. Okay, you cannot say, oh, Thomas, this is my lowercase n. No, it is capital N that you write very small. But that's still population size, however small you write. Okay, in statistic, notation is important. Okay, follow that tradition. But Thomas, I'm not that kind of person. Unfortunately, in statistics, you have to learn that way. Okay, you cannot say that's not your style, therefore you don't want to do it. No. Please respect those people who came before us. If Thomas were the one deciding this, I will not denote it that way. It's not from me. Okay, for the purpose of your study, you better know how people usually denote it. Okay, and follow that tradition. Okay, there are times that we cannot just, we have to live in this status quo. Like capital N is population size. Thomas, do we have to follow that? Unfortunately, in this class, yes. Okay, do you follow that, Thomas? Yes. If I want to teach statistics, I have to use that notation. Okay, not only you have to follow it, I have to follow it too. Okay, now, the way to compute sample mean and population mean are the same. The notations are different, however. Now, suppose we have a sample here. What is the sample mean? Then the notation will be X bar equals to, okay, get the sum. What is the sum? Then you add them, 83 plus 65 plus 91 plus 87 plus 84. You know what? I don't like to do it that way. Let me do it below. Number 8. To find sample mean, I will find the n. What is the n? How many elements in that sample? There are 5, right? 5 elements. 1, 2, 3, 4, 5. Okay. And then the second thing I want to compute is the sum of x. So you add all of those. 83 plus 65 plus 91 plus 87 plus 84. Okay, let's compute this. 83 plus 65 plus 91 plus 87 plus 84. I get 410. Now, because we know it's a sample, so sample mean, I use x bar to be 410 over 5. That gives me 82, I believe. That's how we do it. Thomas, what happens if we don't know that sample or population? If they don't mention if it is sample or population, assume it is a sample. Okay, let me say it again. If it is not known that it is sample or population, you treat that as a sample. Sometimes the question explicitly say it is sample, like this number 8, like this number 10, it says it's population. For number 10, it says it's sample for number 8. Sometimes they don't say it explicitly, but it is implied from the context. Okay, so you say that, well, you know what, these are the scores from Thomas test 1 in his stats class. Now, I have more than 5 students. So if you get only 5 numbers here, then it must be sample. It cannot be the whole number of students, except if I have only 5 students in class. But if you know that I have more than 5 students in class and there are only 5 numbers here, then this must be a sample. That's what I meant by implied. Okay. Now, for number 10, we have population. So how many data there? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so population size, therefore I use capital N, is 9. How about the sum of the data? Oh, this summation notation is basically a capital M block, capital M, that you turn 90 degrees counterclockwise. Okay, That's a capital M that you turn 90 degrees counterclockwise, then it becomes like this. Not E, don't write it this way, no. Okay, not even this, not like this, no, I actually hate this so much. No. Okay, the way you write it, this is horizontal. The top one, the top line horizontal, the bottom line also horizontal. Okay, the one banded like diagonal is this one and this one. Okay, but the top and the bottom lines has to be horizontal. Okay, and not E, not like this. In fact, capital E means something totally different in statistics. Okay, now what is the sum of x? Then I add 1 plus 19 plus 25 plus 15 plus 12 plus 16 plus 28 plus 13 plus 6. Now in my test, you don't need to write this down. You just use your calculator right away. So 1 plus 19 plus 25 plus 15 plus 12 plus 16 plus 28 plus 13 plus 6. The sum is 135. So population mean, the mu is 135 over 9 equals to 15. Okay. I need you to write this. I need you to write this. I need you to write this and this and this. So don't just give me, oh, x bar equals to 82 right away. No, no. I need you to write this, 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 this. Okay. This part here, no need. You can, but you don't have to. Sometimes you worry about your time, right? Thomas, if I don't have time, then what can I skip? The one that I highlight in blue, you can skip that one. The one I highlight in the yellow, you have to show me. Okay. But Thomas, I get the same answer. Why do I have to show the work? Well, let me tell you this. Okay, not only in my class, this is also in reality. Okay, one way for people to lie is by not showing you the detail. So get used to it. Okay, get used to provide the details. On the other hand, if you want somebody to actually follow you, okay, understand you, agree with you, then you should be able to provide them the details. Of course, not too much detail such that you lost in details, but not also too loose such that people don't know how you get these numbers from. Okay, but Thomas, you know what I mean. I know what you mean, but I have to train you to be somebody who can explain these numbers in an understandable way. Okay, now let's see the next question. Number 16. The following data represent flight times in minutes of a random sample of 7 flights from Las Vegas, Nevada to New York, New Jersey on United Airlines. Compute the mean, median, mode flight times. Now, let's see the mode first. I think the mode is always the easiest. Mode is the most frequent data, right? Mode is the most frequent data. Let me sort it first so that I can see it better. I sort it, I put them in order. So the smallest one is what, 260, and then oh, I'm sorry, no, 257 is the smallest one. 257 is the smallest one, and then 260, and then 260, and then 266, 267, 270, 282. Now, once they are in order, then it's easier to see. The mode is the most frequent data, 260. Okay, how about the median? The median is the middle data. Now, the position of the median can be used, we can use the following formula. n plus 1 over 2. Okay, so in this case, there are 7 data, n equals to 7. So the median is at the 4th, n plus 1 over 2. That's the 4th data. What is data number 4? 1, 2, 3, 4. This is data number 4, right? Okay, so the median is 266. Now, how about the mean? Now, for us to complete the mean, you need to first find what is the sum of x. What is the sum of x? What is the sum of x? You add those, 282 plus 270 plus 260 plus 266 plus 257 plus 260 plus 267. That's 4,862, while the n is 7. So this is 4862 over 7. That is 6. Hold on. I typed something wrong. My bad. No. It won't be 4,000 something. No, this is wrong. This is so wrong. This is so wrong. I typed something wrong. Okay, let me do it again. 257 plus 260 plus 260 plus 266 plus 267 plus 270 plus 282. That's 1,862 divided by 7. I get 266. Now, do you notice that earlier that when I use 4,800 something divided by 7, I get 694. How did I know that it must be wrong? Well, because the median must be a number between the largest to the smallest. Okay, the largest number is 282, the smallest is 257. So the median must be somewhere in between. Okay, the median and the mode must be somewhere in between the maximum and the minimum data. Under no situation, the mean will be larger than the highest number. Under no situation, the mean will be smaller than the smaller number. No way. Okay, so that's how I did some little smell test, right? I call that smell test because it's like by some common sense, right? The mean must be somewhere in between the largest and the smallest. Okay, the median must be somewhere in between the largest and the smallest too. Okay. Now here, because it says this is a sample, then the notation for the mean supposed to be x bar, because that's sample mean. Okay. Now, with the time we have, let me ask you to try question number 19. Here we have the data in the next column represent exam scores in a statistic class taught using traditional lecture and taught using a flipped classroom. By the way, the technique of me teaching right now is actually called flip method, flip classroom. So the lecture is basically done by video that you watch that during outside of class time. And during our class time, we actually do it for activities, okay, doing exercise from books or from my old tests later on. Okay, so I think this is a good question, at least to show you traditional and flip method. Okay, now let me ask you to determine the median, the mean and median for each class. Let's just do one of them. Let's just do one of them. Let's do the traditional. I want you to find the mean. I think to find the mean is easiest. To find the mean, to answer this, you need to first find the n, the sample size, and then the sum of the data. Okay, now then later on for you to find the median, you need to put them in order first. Okay, right now it's 5:40. This should take you approximately how many minutes? 5 minutes. Together with our break, let's come back at 5:55. Let's say we come back at 6. Okay, we come back at 6 o'clock. Okay, and you are done with the mean and with the median. Okay, just do the traditional one. You don't need to do the flip one. Okay, see you later. We'll be back at 6 o'clock. So this is what you can do. You can do this problem first and then take a break, or you take a break first, let's say 10 minutes, and then you come back work on this. Okay. Coding. Okay, so I need to find the n first. What is the n? How many data here? 1, 2, 3, 4, 5, 6 times 2 plus 1, 13. There are 13 data, so n equals to 13. What is the sum of x equals to, let me see, there's a chat coming in. The sum of x is 933.6. Can anybody else confirm that for me? I don't do this yet. I don't do this yet. Anybody did it? Okay, so I will assume that's right. Let me do a visual check. Okay, seems to be okay. So the sample mean will be 933.6 over 13. I assume that 933.6 is correct. Okay, and then divide by 13. That gives me 71.81538. Now, in my class, if you watch my lecture, then you have seen that before. In my class, if your answer has more than 5 decimal places, round it to 5 decimal places. Okay, round it to 5 decimal places. In my class, round it to 5 decimal places. Okay, if your decimal is more than 5 decimal places, then round it to 5 decimal places. If you want to make it into 6 decimal places or 7 decimal places, when we say 5 decimal places means 5 numbers after the decimal point. That's 5 decimal places. Okay, now 71.815, that's 3 decimal places. Okay, because there's only 3 decimals after the decimal point. Okay, 5 decimal places means 5 numbers after the decimal point. Okay, if you want to do more, that's okay, but not less than 5 decimal places. So what happened, Thomas, if I have just write 71.815? I penalize you half point. Not big deal, but you should not do it too often. Okay, now how about the median? I need to sort it first. Okay, I start from the smallest one. I think the smallest one is 56.2. And then 63, I think. That's 63.7. And oops, no, 59.8. 59.8, then 63.7. Am I okay now? And then 67.6. 69.1. And then 69.8. Okay, I have some chat coming in. Okay, and then 69.8 and 70.8. Actually, that's a standard way to do it. Okay, you sort it, right? And then I show you the standard weight first. 70 and then 71.5 and then 78.2, 80.9, 81.3, 85.5, 85.3. Do I have 13 data here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm missing something. What do I miss? 81.3 is done. Oh, 79.4. 79.4 is here. 79.4. Okay, now it's 13. Okay, now then I use my formula. There are 13 data plus 1 becomes 14 divided by 2. That's the 7th data. So data number 7 will be 1, 2, 3, 4, 5, 6, 7. This is data number 7. Okay, so the median is 70.8. Now, if you think about it, then you actually don't need to do it that way. In my test, you still need to show me the sorting. Okay, in my test or my quiz, you still need to show me the sorting. But if you just want to show, want to do it fast, then you do this computation first. Okay, you do this computation first. Oh, data number 7, position number 7 is the median. Okay, so you start counting from the smallest one. The smallest 1, and then 2, and then 3, and then 4, and then 5, 6. So this is data number 7. Okay, without actually sorting it. Now, the reason I show you to sort because the following. In reality, when you do, let's say you do this problem, and let's say we don't have, no, it's not like 13 numbers. Let's say we have, huh? Hold on. Do I make a mistake? 71.5. Is the median 71.5? I don't think so, though.
No, Professor, I was helping with the ordering.
Oh, okay. Thank you. Yeah. In reality, let's say if you have 300 data, right? And then how will you find the median? What you usually do is you enter all those data into Excel, and then you sort it. Okay, so let me show you Excel. Give me a second. Excel is a software that I think you should be able to be proficient with by just watching some videos on YouTube. Okay, but you need it though. Okay, you need it. Okay, let me show you how to use Excel, at least a simple one. And I believe most of you know how to do this. Let's say I type random numbers, okay? Now then, basically, you put them, you sort it, right? You highlight those, and then you sort from smallest to largest. That's it. Okay, so right now we have 10 data, right? Like the one we have here. We have 10 data. After I put them in order, 10 plus 1 is 11, divided by 2 is 5.5. So 5.5 means the median is 5.5 data, which means the median is the average between data number 5, which is 3, plus data number 6, which is 4, divided by 2. That is equal to 3.5. Okay. If the median is between two numbers, like in this case, the median is between two numbers, then you need to show this procedure here. You have to show this. Okay, that it is between 3 and 4. So 3 plus 4 divided by 2. Even though you and me know, well, the midpoint between 3 and 4 is 3.5, but you still need to show that procedure. Okay, now please don't tell me, Thomas, I can do everything in my head. If you can do it, I can do that too, right? But the issue is not, can you do that in your head? The issue is, can you show what you do in your head to your listener, to your audience? Okay.
Professor Thomas,
Yes.
can we go back to medium? Because I think I was a little lost on there. I got 7. Oh, crap. I didn't get 933.6, and I was wondering what I did wrong. I got, I think 733 point something in that. I'm trying to figure out where I went wrong at.
I honestly don't know. Just add them. Okay, let's try. So I show you my calculator here. Okay, give me a second. So basically what we will do is we add all those numbers. 70.8. I will add the first row first. Okay, 69.1 plus 79.4 plus 67.6 plus 85.3 plus 78.2 plus 56.2 plus 81.3 plus 80.9 plus 71.5 plus 63.7 plus 69.8 plus 59.8. Let's see what's that. Yeah, 933.6 happen to be okay. Yeah, it's the. So take a look on when you add on your calculator. Maybe you're missing a couple numbers, right? That's how we check that. Okay. At the beginning of your career in entering data into your calculator, it's actually quite common for you to have that case though, that you type a wrong number and you don't realize it, or you're missing one number and you don't realize it. But after some practices, then you should be okay. Okay. I will teach you more how to use this TI-84 in entering data and get those numbers. But in my test or in my quiz, I require you to show me that way. Okay, I require you to show me this way of showing work. I need you to show me this. I need you to show me this, and of course this, and then this, and then this. Not just suddenly come up with, oh, X bar equals to this. Don't ask me how you get it. I use calculator, Thomas. No, I know you must use calculator, but I want you to show me what you did with your calculator to get that. And the way to show it is like, I get this, and then I divide them. This is the notation, this is the result. Okay, we are not at the place, I don't teach you yet how to use calculator by you enter the data and let calculator compute everything for you. Because what? Later on, when you look for a job, okay, and your boss, the person who interviewed you, asks you, hey, Thomas, this is the data, find the sample mean. You don't tell them, can I get a TI-84? They give you TI-30 and they say, no, I can only use TI-84. Okay, and then when they don't hire you, you then file a complaint because they don't allow you to use TI-84. It's like, no, you have computer. I give you computer. That's a lot more powerful than TI-84. Okay. Don't tell me that, what is the best way to say? TI-84 and computer is a lot more powerful. So the thing is, computer basically available in every office right now. Okay, but not TI-84. Okay, and every computer, almost every computer, if not all, has Excel in there, or a program, a software that is like Excel. Okay, so if I give you Excel and you insist on using TI-84, you just tell me that you are not qualified to be my employee. Okay, I know I will not hire you because you insist on your way even before I hire you. Ta-da! Strange. Okay, anyway. Part B asks a conceptual question. Suppose the score 59.8, that 59.8 was misrecorded as 598. How will this affect the mean? Of course, because you give a larger number as supposed to, I mean, compared to the supposed one, then your mean will be higher, right? But it will not affect the median by big time. Okay. In other words, mean is more sensitive to outliers. In other words, if you suddenly have a very big numbers that is very, very big compared to the rest of the data, then the mean will change significantly. The median, however, the median is less sensitive to outliers. Now the median may change, but it won't change that much. Okay, the median may change, but it will not change that much. Okay, you can try if you change this, for example, this one here, right? So I change this, becomes 598, becomes 598. Okay, so data number 7 will be 1, 2, so because I skipped that one, right? 1, 2, 3, 4, 5, 6, 7. So the median will be 71.5, which is not too much different from the actual median. The actual median, if there's no mistake, that will be 70.8. Because of this mistake, then the median becomes 71.5. But that's not very big difference, right? Compared to the mean, if you change that 59.8 becomes 598, then the mean will be very, very different. Okay, so that's the property. Under what situation, Thomas, we should use median? Under what situation we should use mean? Now, we should use mean. We should use median if you see the data is skewed to the right or skewed to the left, that you have some numbers that is quite extreme, then you better use the median instead. Okay, let me fix this 59.8. Okay, the last question from this section. Mitsuzuro finds the mean height of all 14 students in his statistic class to be 68.0 inches. Just as Mr. Zuro finishes explaining how to get the mean, Danielle walks in late. Danielle is 65 inches tall. Now, what is the mean height of the 15 students in class? So originally, okay, n equals to 14, okay, and then the mean to be 68. Okay, now then with Danielle, count it in, what is the new mean? But for us to find the new mean, we need to know the sample size right now. Okay, right now, how many people with Danielle? Then it becomes 15, right? Okay, but what is the sum? Okay, now we will get the sum this way. What is the original sum? We know that the sample mean is the sum over count. So 68 equals to the sum of x over 14, right? So the sum of the height before Danielle coming in is 68 times 14, which is 952. Now, that's the sum of the heights before Danielle coming in. Now, once Danielle coming in, then the total height will be 952 plus the height of Danielle, which is 65. That will be 1017. 1117. Oh no, 1000, that's right, 1017, my bad. 1017. Okay, so the mean will be 1017 over 15 now. That's 67.8. That's the sample mean. So think of it this way. Originally, you have what is n, what's the sum, what is the x bar, right? Now then, with Danielle, 14 becomes 15. Okay, now for us to find the x bar, which is originally 68, we need to know the sum here. Okay, whatever the sum you get here, you add the height from Danielle. Okay, so from here you get this, from here you get this, from here you get that. Okay, now that's for 3.1. The type of data we get so far presented to us in the sense of raw data so far, raw data. Okay, and even 3.2, the data still provided to us in raw data. Now, population variance. Denoted by sigma squared. It's like a lowercase o with some hair. Not like this, not theta, no, not this one. Okay, not that one. Theta is different from sigma. Sigma is like you wrote clockwise lowercase o with some hair. Okay, now population variance, you square that. Okay, now our textbook gives a formula for population variance. No, actually they don't. They give the standard deviation and then the variance. We will not use that formula. Okay, we will not use the formula provided by our textbook. I will give you definition formula. You know what, let me write it this way. Definition formula. Population variance is the sum of data minus the population mean being squared over n. The average of the square of the errors. Now, even though that's the definition formula, we will never use that formula to compute variance in our class. Okay, we will not use that formula. Which formula we'll use? We'll use computation formula. Now, computation formula that I give you here looks different from the one in our textbook. Okay, maybe I prefer to say the formula given in our textbook is different from the one provided in every other textbook. I don't know why they write it so strange way. Our textbook write it this way: the sum of x being x squared minus the sum of x being squared over n big over n, like this. What the heck? Why do they like? Why does he like complex fractions? I wonder why. No, we will not use that one. I will use this one. Okay, I will use this one. Now, computation formula actually consists of three parts, three numbers that we will get first, capital N, that's the number of data. The sum of X, that's the numerator of mean. When we compute population mean, right? The numerator is the sum of X, right? And then the third number is the sum of X squared. Okay, that's the population variance. Let's say I do number 7. Let's say I do number 7. Number 7. Okay, that's population, right? That's population. Now, when I need to compute the variance, I need to first know capital N. What is capital N? How many data there? That's 5. Okay. And then how about sum of X? Sum of X, you add those numbers, 3 plus 6 plus 10 plus 12 plus 14. 45. Is it right? 36 plus 9, 45. Now, the sum of X squared is each of those data being squared first, and then you add them. Okay, so this notation, the sum of X squared, the sum of X squared means for each data, you square first, then you add them. I get 485. Okay, some warning. Sum of X squared is not the same to the square of the sum. No, it's not. When you square this 45, when you square that 45, you get 2025. The sum of X being squared is 45 squared. Okay, now it's different from the sum of X squared. It's different order operations. What happened on the right-hand side here, you add first and then you square it. Okay, the one on the left-hand side here is you square each data first and then you add them. Different order operations. Okay, yeah, one of them, it's just different order operations. So you add first and then you square, and you square first and then you add. Okay, I usually joke this way. That's, you know, what's the difference between Thomas and Superman? Superman has his underwear outside. Okay, now if you see somebody with his underwear outside his pants, don't laugh at that person. Who knows that person can fly? Okay, now you get these 3 numbers first. Now, once you get these 3 numbers, then you proceed with, let's say, for example, I want to find the mu. The mu will be 45 over 5, that's 9. And the sigma squared, the population variance, will be, on the top left is 5, the first number, times the third number, 485, minus the middle number squared. Over the first number squared. Okay, 5 times 485 minus 45 squared divided by 25. So sigma squared is 16. Now, population standard deviation is the square root of that variance. Always. Population standard deviation denoted by sigma is the square root of sigma squared. In fact, all standard deviation is always square root of variance, regardless if it's population or if it is sample. Okay. Now, how about if we have we need sample variance. Sample variance is very similar. The notation is S squared. Okay, definition formula, which we will never use. S squared equals to the sum of the square of the errors of each data divided by n minus 1. So if you compare with sigma squared, it's very similar. The sum of x minus mu, instead of mu, you change that to x bar over capital N, but this capital N becomes n minus 1 for variance. Okay, in my lecture, I believe my lecture number 3 especially, you will see a good nice table to compare the differences between those formulas. Okay, now and then the computation formula, the one we will use. S squared equals to, on the numerator, n times the sum of x squared minus the square of the sum. So the numerator is very similar to the formula we have in population, divided by n times n minus 1. Okay, so suppose if I look back to number 7, but instead I call that a sample. Suppose it is a sample instead. Okay, then instead of capital N, I use lowercase n. It's still 5. The sum of x is 45. The sum of x squared is 485. Now then, what is sample variance? Sample variance will be, on the numerator, it will be the same. 5 times 485 minus 45 squared. First number times the third number minus the square of the middle number. Now the difference is on the denominator. Instead of n squared, it will be n times 1 less than n. Okay, so that will be, what's that? 5 times 485 minus 45 squared divided by 20 instead. So the variance is, sample variance is 20. And sample standard deviation, S, will be the square root of 20. In 5 decimal places, 4.4721356. So it's like 359, that's like 40. Okay, sample standard deviation is the square root of sample variance. Okay. I think I will not cover this today. I will do it on Wednesday. Let's see this question here. Same question we have from 3.1, but this time we want to see which is has more dispersion. So the purpose of standard deviation and variance is to measure how the data varies from the mean. Okay, it's basically like this before we really do number 17. right? Before we will do number 17. Let's consider the following situation. Let's say A take 3 tests, and his test score were 80, and then 90, and then 85. Compare this with somebody whose test is 85, and then 70, and then 100. Okay, you will see that these two data here, these two people have the same mean. Okay, the n here is 3. The n here is also 3. The sum of the data here is, what's that, 170, 255? Okay, the sum of the data here is also 255. So if we look at the mean both of them are 85. Right? Maybe I write properly how I get that 85. The mean will be 255 over 3, which is 85. 255 over 3, that's 85. Okay, now the thing is then, the next question, which student has actually is more stable? Which student is more stable? Now, of course, visually you can see that the data for A, the mean is 85, okay, and then it has 90 here, and then has 80, while the one here, 85, 100, and then 70. So clearly, B varies more, right? B varies more. B deviates more from the mean compared to A, even though they have the same mean, but A is more stable. B has more variations. Okay, now the purpose of finding variance and standard deviation is to quantify our feeling that B varies more. Okay, so our feeling is right. Okay, our feeling is right that B varies more, but the thing is, like, what happened is the variation is so close that we cannot decide by feeling. Okay, the thing is, feeling can never be used as an evidence. Okay, that's why we need statistics. Statistics quantify our suspicion. Okay, like B varies more. Why? Let's look at the variance. Okay, so let's find out what is sum of x squared. Sum of x squared is 80 squared plus 90 squared plus 85 squared. That's for part A. That's 21,725. Now the sum for x squared in part B is 85 squared plus 70 squared plus 100 squared. I get 22,125. Okay, you don't need to show me this. In your test, you don't need to show me this. Just give me the result for that sum of x squared right away. Now then, the variance for A will be sample population size times the sum of the x squared minus the sum of x being squared over population size being squared. While the one here, population variance for B will be 3 times 22,125 minus 255 squared over 3 squared. Now you can compute this further and you will see that B is greater. Now because the variance for B is greater, it means the data in B varies more compared to A. Okay. Now, do not underestimate this, though. Do not underestimate this. The use of this variance, and therefore standard deviation if you take the square root. Now, these two students, if they both of them come to see me and ask me, Thomas, we have the same average. Should we have the same chance to get an A? The answer is no. Even though they have the same average, 85, let's say this is their test 1, 2, 3, and they have final coming. Okay, so will A have a chance to get an A? Yes, A have a chance to get an A. B also have a chance to get an A. But comparatively, because the average is 85, which is a B, therefore, and the standard deviation for A is smaller, means A tends to deviate not far from 85. That's the case for Mr. A. Okay, because the standard deviation is smaller, then even if his final will not go too far from that 85. Compared to B, B has the same average 85, but B once get 100%, even though at the same time, once B get a 70, which is a C. But this B here deviates more from the average, so B has a better chance to get an A compared to Mr. A. With the same mindset, then B has a better chance to fall down to C compared to Mr. A. Mr. A is quite stable at 85. So I can bet like $100 if I get this kind of students. I can bet with $100 that in the end, Mr. A will end up with a B. Why? This person is like get a 90, it's like barely an A, and 80, that's barely a B, and middle 85, middle B, right? So with what I see here, then very likely this person gets something around 80 something anyway. Okay, so when I grade this person's final, if I get 84, that person get 84, then yeah, it confirms the person is supposed to get a B. In other words, when I grade Mr. A, I do expect this person get a B. While when I grade Mr. B, I need to be more careful. Why? Because this person have our largest standard deviation. He may do very, very well in the final, but he can also bomb his final. Okay, this person can do very, very well, but also did quite poorly sometimes. While Mr. A, on the other hand, is quite consistent around 80s to 90s. Okay, so even though they have the same average, when I talk to them, okay, the probability that who will get an A, who will get a C, will be different with what I tell Mr. A and what I tell Mr. B will be different. Okay, so how do we know which data? How do we quantify the dispersion, the variation, how the data varies from the mean? We use variance and therefore standard deviation to compute it. Okay, now part A here. Which course has more dispersion in exam scores using range? So for part A, the range is the largest number. So range is easy. What is the largest number for part A? 85 something. 85.3 minus the smallest number is 56.2. So that's 29.1. Okay, for the flip, you know what? Let me use traditional for traditional. This is the flip one. By the way, the word flip is actually an F word, right? Do you realize that? So the flip class, the highest score is 91.8. But the smallest is 63.4. Okay, so it will be 28.4. And that's for part A. Now part B, which course has more dispersion in exam score using standard deviation? Basically what we did here. Oh no, yeah, the same procedure with what we did here. So what you need to do is from the traditional part, you need to find the n, which I remember is 13, the sum of x, what was that? Let's see. 933.6. And you need to find the sum of x squared. Now then, for the flip class, you need to find the n. I think it's also 13, huh? Yeah. Okay, you need to find the sum of x, and then the sum of x squared. Okay, now then, from there you compute the variance for each one of them. Actually, once you compare the variance, the result which group is greater will result in the same conclusion when it comes to the standard deviation. Okay, there are a lot of numbers to compute though, so I don't really want to, honestly, I don't really want to do it. It's just too much. You know what? I still have around 10 minutes. Let me just go on with the traditional one, and at home you continue this work with the flipped one. Okay, so we already get the sum of x for traditional. I will do the sum of x squared for traditional. 70.8 squared plus 69.1 squared. You know what? Let me do it this way. I will use my online calculator so that you see what I did. 70.8 squared plus 69.1 squared plus 79.4 squared plus 67.6 squared plus 85.3 squared plus 78.2 squared plus 56.2 squared plus 81.3 squared plus 80.9 squared plus 71.5 squared plus 63.7 squared plus 69.8 squared plus 59.8 squared. 6798386. 6798386. Okay, so then the variance will be the first number times the third number minus the middle number square. Give me a second, I'm sorry. Okay, over 13 times 1 less than that. Okay. My son is still 4 years old, by the way, so please forgive his ignorance. he get too much into himself at times that he forgot that I'm teaching. And sometimes he wants to get your attention too. He likes to suddenly show up on my screen before and say hi to my students. Divided by 156. So when I compute this, I get 78.08474. Now then, the standard deviation will be the square root of that number. Okay. And I add the, so I get this right. So 13 parentheses, 13 times 67,983.86 minus 933.6 square. Now I close the parentheses for the numerator, divided by open parentheses for the denominator, 13 times 12. Okay, so 78.08474 to 3 decimal places, right? Now then I will do square root of that number, square root of that answer. Second answer. So the answer that I use here, always the answer from the previous one. That's 8.836557. So 83656. 8.83656. Okay, now what we learned today. To summarize what we have learned today, okay, we learn what to pay attention to when watching lecture videos for chapter 1 and chapter 2 from my announcement tool. No, I'm sorry, announcement number, oh yeah, announcement number 2. Is it right? Or announcement number 3. I somehow kind of forget that. Yeah, announcement 2. Okay, and then second, given raw data, basically the data is not put in the frequency distribution yet. Okay, basically they just give you, oh, these are the data, like those 13 data we have up there. Okay, given raw data. Okay, find n or n, depends if you get population or sample, the sum of x, the sum of x squared, to further find the sample mean or population mean, sample variance or population variance, sample standard deviation or population standard deviation. Also to find the mode, the most frequent data, and the median, the mean, the middle data. Okay, now so please practice at home. You can just use my examples that I have here and the one from my lectures, the lesson 1 and lesson 2. Okay, but median is important because in your lesson 3, as I remember, you will learn to find first quartile and the third quartile. Now on Wednesday next week, Monday we don't have class. On Wednesday next week, we will discuss lesson 3, basically what happened if the data is given in group data. Okay, so at that time, I assume you already watched lesson 3. Then we do problems from 3.3 and problems from my previous quiz. Okay, see you then. Bye-bye.
Professor, one question.
Yes.